All right, so today's lecture is about, well, it's going to be a slightly different perspective than what we've been focusing on for the last few weeks. So for starters, we're going to be focusing on just basic Boolean logic type stuff. We discussed logic a little bit when I used circuits as an example of a DAG. But I mean, you know from programming that you have Boolean variables, you have true and false, true or false, and then not, right? True becomes false, false becomes true, right? Those are just our three basic things. So, okay, suppose you wanted to write exclusive OR in terms of just these three primitives, and, or, and not, okay? So that means the XOR of x1 and x2, it should return true only if exactly one of them is true. If they're both true, you should return false. If they're both false, you should return false. Any ideas? Yeah. Oh, okay. X and Y. Oh, sorry, say that again. X or Y and not X or Y. What did I write? Oh, I did it opposite way. Well, first of all, we're doing X1, X2, but that's okay. Let me first write down what you wrote as well. So X or Y and this is maybe better too. Okay, so that's another way to do this. Okay, so let me go over the suggestion first. Okay, so X or Y and not X or not Y. Is that correct? I'm just kind of spot checking. So the first clause is like, okay, at least one of them needs to be true. And the second one says at least one of them needs to be false. And then out of two of them, the only way to get one and one is exactly one true, one false. So that seems straightforward. The one I had prepared is almost like enumerating the two possibilities. So the first one, x1 and not x2, is only satisfied if you did true and false. And then the second one, not x1 and x2, is only satisfied if you did false and true. So there I'm just enumerating kind of the two assignments that would make it true. I think they're both kind of readable. As you know, any kind of parenthesized system, but you can also envision these formulas as like a tree. Okay. All right. So good. Here's a harder one. Anyone want to figure out how to add up 2 bits? So, okay. So let me say, so your input bits will be x1 and x2, and your output bits will be x3, x4. And I want to make a formula that evaluates the true. It's sort of like x1 plus x2 is equal to x3, x4 in binary. X3 needs to handle the carry. And otherwise, will come out to false. So it's more like verifying an addition. Yeah.
You do the same trick again, like you have x1 and x2 and x3 and x4 or
Oh. I see. So one option is to do that truth table-ish thing I did on the XOR, which is to enumerate all the possibilities that would evaluate to true, and then put a bunch of ORs in between. So I won't write it out because it's sort of long, but in this solution here, I kind of encoded the two things that would satisfy it as an and. It has to be true and false, or false and true. And then I just put an or saying, any of these are okay. So it seems like you could probably always do that. So for this, there's some combinations of x1, x2, x3, x4 that are correct and some that aren't. Right? I guess 2 to the 4 possible combinations, and you can kind of enumerate all the assignments that evaluate the true. Each of those become an and, saying, look, it has to be these 4 values in particular. And then you kind of put an or in between to connect all of them. I had somehow come up with something different. I think it was different. Okay. Somehow this is supposed to be x1 plus x2. Okay. This would just be another example. I think I was trying to think of an example that was deep, even though you can always do this enumeration trick. So if you want to visual, I mean, there's no way you would be able to come up with this, at least without the assignment trick. But if you want to visualize it, it'll look something like this. Okay. It's just supposed to be a non-trivial example. Yeah.
So isn't the equal to operation not something we could like check if, like for example, x1 and x2 is equal to x3?
So we'll kind of come back to that. Yeah, actually, just hold that thought. That's a good question. That's a great question. Okay. Oh, it's right here. Okay. So, all right. So, okay. So we Boolean logic. You just kind of propagate the values, it evaluates to something. But here I want to try to suggest that, and maybe it's not a surprise to computer scientists like you, but Boolean algebra can be very expressive. Right? Maybe it's not surprising because at the bottom level, your computer is ultimately a bunch of Boolean algebra, and at the top level, you can do quite a lot on your computer, right? Even AGI or something. But anyway, so to this point, what I would like to do is come up with formulas that will model, sort of like programming primitives. Okay. So first would be a formula for z equals x. So this should be some, Boolean formula of z and x that comes out to true if z is equal to x and comes out to false if z is not equal to x. That's sort of been like encoding assignment, right? Because saying z and x have to be equal. Okay. Yeah.
Maybe just do the negation of the previous XORs.
Okay, yeah. Can you negate the XOR? It should be the opposite of XOR. So I negated it like this. So yeah, equality should be the opposite of XOR because XOR is different, right? So if you negate this whole thing, right, then what do we get? What does it start to look like? How do you negate a Boolean formula? Yeah, how do you reduce? Yeah, so what is the Morgan's law again? Wait, is it the Morgan's law? What's the one for distribution? Is that also the Morgan's? Or just all the Morgan's laws? Okay. It's nice to be named after something. Okay. So which of the Morgan's laws then?
It's all, but just
Well, I don't know the number, but what happens? Like,
flip the negation size of each variable and then flip the sign for it.
okay, so is the first step like this? So I flipped the. Oh no, I got it wrong. You flip the thing in the middle, and then you negate the two arguments, and then you keep going. It might look messy with these, but you can just verify for two variables that it's okay, and then otherwise it's okay. And then you go down further, and you do the same thing. The signs flip. Or x bar 2. Okay, so let's see if we can interpret this. So here you're saying not x1 or x2 and x1 or not x2. How do I interpret that? Okay, so if they're both true, then it'll be okay. You'll get one from each. If they're both false, you'll get one from each. If you have like a true and false, then whichever one of the two will come out false, false. Okay, so all right, so that's one. That's one way. Let's see what I had. I guess I had this version, which may or may not be more intuitive. I think the other one's coming up in a moment. Either both true or both false. I think this is just enumerating all the working inputs. Okay, so at some level you can do assignment, right? Because x could be some complicated expression. It can be a bunch of stuff in parentheses. And you just want to say, I want to make z equal to this whole Boolean expression. Then you can kind of plug in for z and x here, right? And that forces z to be equal to whatever x is. Okay, What about if x, then y, else z? Right? Conditionals are primitive. So I want to come up with some Boolean formula where if x is true, it returns whatever the value of y is. And if x is false, it'll return whatever the value of z. Yeah. Oh, all right. X and y, or not x and z. So what's the intuition here? Yeah, and I feel like here it's almost like x is acting as like a switch, right? So you're going to take only one of them, but if x is false, then it sort of throws away everything here, and if x is false, then it'll keep this, right? So you kind of see x acting as almost a switch at the beginning of the two clauses. I think that's what I had. Yeah, I had the same one. Okay, so. But the point I want to make is these are almost like you can start imagining putting a whole programming language together where you're like awkwardly trying to do some basic thing, but you're just expressing it with Boolean algebra. And so Boolean algebra is arguably quite expressive. Once you build up like a whole language, I think that's how I figured out the addition one. Was I just like wrote out some thing and I started plugging in, and that's how I got that complicated Boolean formula from before, just plugging in if-else stuff and assignments. Okay, so there's more than maybe meets the eye. Now the problem we're interested in today is called Boolean satisfiability. So as input, I'll give you a Boolean formula. Okay, some bunch of parentheses and n variables and ands and ors. There'll be n variables. Maybe the size will be like basically the total number of symbols in the whole thing. Or if you visualize it as like a tree, how many total nodes, something like this. And the goal, the goal is, I give you this formula, and your goal is to decide if there's an input that makes it output true. So I give you, some complicated looking thing. You don't really know the origins of this formula, but otherwise you have all the information in front of you. And the question is there any way to satisfy it? Satisfying meaning you make it evaluate to true. Yeah.
You could try all possible combinations. So it'd be 2 to the n combinations and evaluate the function and see if any is true.
Okay, this is a very important point about this problem. At the very least, we can always try all possible inputs. Because, so this question of trying to find a solution is one question, but the question of just evaluating a formula is not so hard, right? If I gave you the values and you just had to plug and churn, you can write some quick script to do that. That's not so hard to do. So since you can always evaluate a circuit, you can at least plug and play. And I think, okay, well, I'll come back to that example in a moment, but at the very least, you can always brute force. Okay. But hold that thought for just one moment as I work through this example, which is just take this formula. It's just 2 variables, so it's relatively simple. Does this one have a satisfying solution, just to make sure we're on the same page? Okay, I saw some no's, but why not? Yeah. So I've enumerated all 4 combinations. I mean, I chose an example that's going to be easy to verify, but I've enumerated all 4 combinations of x1 and x2 with their negations. So no matter how you set x1 and x2 to be true or false, there's going to be one of these that kills you. If you did true, true, this one will lose. If you did true, false, this one will lose. You can't get all of them. If I picked any 3, I think it would be just fine. In fact, whatever's omitted is sort of the key to a satisfying formula. Okay. In general, it's not obvious that you can look at it is true that if you find a satisfying solution, you can double check it's correct, right? It's not really obvious in a general case that you can take a formula and be really confident that there's no satisfying solution. This example is sort of anomaly because it's symmetric and enumerating everything. But in general, if someone told you, oh, you can't satisfy this formula, it's not obvious how you can kind of prove it. Yeah.
This is just like x1 equals x2 and x1 equals. It's just not.
Oh, okay, that's true. If we, that's maybe also another way. If we go back to our kind of programming language point of view, this one is saying that both x is equal to x1 is equal to x2, and x1 is not equal to x2. So yeah, you might be able to sometimes, interpret and really identify contradictions in a formula. Yeah.
Think of each operation as like removing some possible input states, and can you figure out if it's satisfiable by saying if all the input states are removed, then it's not satisfiable.
Yeah, so I think we should just go to the next slide. So the real question is, what's the algorithm, and is there an algorithm? Let me just set it up a little bit, and we'll come to this point. Okay, so this point about brute force, touches on something important. So this is an algorithm where, this is a problem. It might seem a little opaque because of Boolean algebra and stuff, but it has this property where if you stumble on or you have the right answer, you can verify it's a right answer, right? So if you have a satisfying assignment, you can plug it in and see, yeah, it is a satisfying solution. So it's a search problem in the sense that you're looking for something that you can recognize. You're looking for a satisfying solution. And if you do find it, you can recognize it, right? It's very easy to write an algorithm that plugs it into the formula and evaluates it. So in that way, it's almost like that over-under binary search game. You're looking for something, but the key property is that you will actually recognize it if you find it. Okay, not all problems are like this. So as was already noted, you can at the very least try everything. Okay, and we can dig into this conversation. Although it's a search problem, in that sort of lifted generalized sense of the word lift or search, it's clearly not as obvious as the over-under game. I think that's not a controversial statement. Okay, so now the big question is there a polynomial time algorithm for this question, like we did in the past few weeks? Okay, so I thought that, okay, good, ideas. So maybe what I'll do first, this always makes me feel like I'm teaching, is I'll first solicit a vote from all of you. Okay, so the question is, do you think there's a polynomial time algorithm for this question of SAT? Okay, and you're allowed to not vote or vote yes or vote no. So first, who's not voting? 1, 2, this number goes up over the course of the semester. We're up to 5. Okay, who thinks that we can come up with an algorithm? I would say most of us. Okay, and who doesn't think we'll have an algorithm? I must have made a mistake. Okay. Okay. All right, so good. Those who voted yes, what are some of your thoughts, some of your instincts, reasons for being optimistic? Yeah.
If you think of each operation as acting on like the number of states that could evaluate true, then you can just kind of run through iterations, kind of like the divided conquer method.
Okay, so if you think of each operation as what again?
So I mean, like for example, like x1 and x2 means that we basically from the all 4 possible cases of x1 and 2, we remove some of them. We remove all they're of 1, and so now we basically are away at the possible states of the input vector.
Okay, so can I imagine an algorithm where maybe I try plugging in x1 to be true or something, right? And then I start like eliminating a bunch of stuff. That's not going to help me. That one's already satisfied. That one's not going to help me or something, right? It feels like one can make sort of discrete progress in the sense that the formula is shrinking.
Not quite what I was thinking.
Sorry?
Not quite what I was thinking.
Oh, okay. Well, but it feels like, well, maybe one thing is that it certainly feels like some discrete thing that a computer can manage, at the very least, right? Yeah.
This recursively because like within an and statement with the brackets, you can do it recursively to check what satisfied this and statement, and then check if it satisfies the other and statements. If it does so.
Okay. So I think this is an algorithm, if I understand correctly, I'm looking at, something like a tree here. And why don't I try to do some kind of recursion like we've been doing? And, I can think of like these two problems. I guess this is an or, so it's not so interesting. But you just need to figure out one side or the other in this case can be evaluated, right? So this you can recurse on. And then if I move to this tree here for this subproblem, now it's like, okay, why don't I recursively try to figure out if this tree is satisfiable separately from this tree being satisfiable, and then like compare the satisfying solutions or something, right? Certainly if they come up with the same satisfying solution, then I know the whole thing can be satisfying. Now, the obvious issue, of course, is that satisfying this side alone without any consideration about the other can be misleading, right? Maybe this is satisfiable, but you can't do it with this, and you want to take this into consideration. So although they look separable in the tree, right, x2 is appearing on both sides here. x1 is appearing on both sides here. So they're not as cleanly separated, just because they can divide the tree doesn't mean we're really dividing the variables. So it's not as separable, it's not that straightforward, yeah.
So the idea that I'm thinking of is kind of along the same lines
Uh-huh.
as what we talked about here, but about seeing if each different side of the tree is satisfiable. More so just seeing what values can be equal and set those as assumptions for the rest of it, right? And then if those ever point to one another, then you know that's not satisfied.
Okay, so, but at some level, I'm not going to do this straightforward, just trying to plug in a satisfying assignment from here to here or something, but can I deduce something here, make some progress and still share that over?
For example, x and y and not x and not y, then for and, you need to go down both sides, but for the left one, you need x to be true, and for the right, you need x to be false, and then those assumptions are applicable ones, so it's not possible, right?
Yeah, and I think this problem has this feel where it feels like, isn't there like a lot of things where you can stare at it and say, well, it must be this or that, and you make some progress, this or that, and make some progress? Doesn't it feel like you can be clever? Yeah.
If you could solve this problem, then we showed that with Boolean logic, you can kind of express almost every problem, right? So you have all these statements. So then wouldn't you be able to solve almost any math problem if you could do this?
Okay, so this would be an argument on the other end. So if, for example, we took our SAP programming language to the extreme, once I do if else and I'll do addition and I'll do loops and I'll do this and that. I build up a whole Pythonic language, using just SAT formulas and assuming they're all kind of not too big on you. Okay, well then suppose I could solve SAT and I could basically program in SAT. What are the implications of this? Yeah.
Well, the Boolean size by voting problem is equivalent to basically every NP problem.
Well, let's try to reason from first principles.
It would basically, because the SAP programming language lets us express basically like any math problem, which we can by extension use to represent any sort of decidability problem as well. It would imply that we would be able to solve any problem at all in time that we could check all.
Like if you could solve SAT, what would be a really quick way to make a ton of money? Bitcoin. Yeah, we just figured out how to basically SHA-2, if we can just get that written in SAT, right? And we'll just figure out how to reverse engineer SHA-2 and get the next, however that thing works, right? You can take all the Bitcoins if you can solve SAT. Okay, so that's one argument against, yeah.
Why is it though that if you're just checking whether or not it can result in true, it doesn't necessarily mean that we're solving the problem?
Good question. Okay, so we're also only interested directly in the yes/no question. And if you wanted to take all the Bitcoins, you'd actually have to come up with the key that, whatever, gets you that hash, right? Yeah.
they use that as an example is like 3n plus 1. If you have if else and then while loops, then you can define that. Like, oh look, there is a solution, but you don't know if there's a solution to that problem. So
3n plus 1.
yeah.
Nicolas conjecture.
I don't know. 3n plus 1 doesn't, I don't know what that, okay, but ABC conjecture, whatever else. Yeah.
There's a way to keep like reducing, I guess, like the bracket simplifying the equation to some form where you're eventually be able to like derive a function. So that's something.
But this is back into coming up with an algorithm. Okay. Now let me get to this one question that was mentioned. Okay, suppose we could answer the yes/no question, right? So you have something that can solve and reverse, in some way solve any SAT formula, and you want to get all the bitcoins. That means you actually need to find a satisfying solution to a given formula. Okay? Any ideas? So all you know how to do is yes/no, and now we want to actually solve sort of that constructive version of the question. Yeah. Okay. You want to expand? Like, what would you actually do? You have this black box that you can give it a formula, and it'll just answer yes or no, and it's reliable and it works. And okay. How would I actually do that to actually get a solution? Use that as a black box. The black box metaphor is very clean, right? Because then you can't cheat.
You have access to the actual formula.
Yeah, you have the formula. It's all written out in front of you. You can look at the SHA-2 code. It's all there. Yeah.
Maybe like binary search your inputs.
Binary search your inputs. Are you going to think of like an n-bit string as like a number between 1 and 2 to the n? So you guess some number in the middle, that's some bit string, and it says no. Are you going to go left or right?
Like your what you pass in if it's like greater than.
So our black box only says yes or no. It doesn't tell you less than, greater than, or equal. Yeah.
So refining what I was thinking earlier, you take an array, bubble it to the n possibilities, and then if you think of one operation, let's say like z equals x, then that one goes and sets to 0 all of the possible inputs where z does not equals x, and then so now you have like that list of possible inputs that could get like give one from that one operation, and then when you combine on the next like level up, then if you have an and, you multiply them together. If you have an or, you add the two like input vectors together, and then you kind of just recursivate out the tree that way.
Yeah, but I do want to stress we're looking for a polynomial time algorithm. And your very first step was to allocate an array of size 2 to the n. It's like once we're at whatever 280, there's like atoms in a universe, right?
In parallel, though, you can definitely do that in like time.
It was 2 to the 280 computers. There's 2 to the 280 atoms in the universe. How are you going to parallelize? Was there another? Yeah.
So let's say we want to verify an operation that is a 1 and 0.
Uh-huh.
Just substitute all of, let's say it's called x1, substitute 1 for all the x1, let's see if that's all that's happening, right?
That's right. So if you have only a yes/no machine, you want to get a solution, right? There's something called like I did the name like self-reducibility. It doesn't really matter. You just plug in x1 is equal to 1, right? And then you evaluate as much as you can, and you get a smaller formula with some things kind of disappearing, right? And then you check to see, okay, if I plugged in and I have this residual formula, is that still satisfiable? If yes, okay, you chose a good one. If no, it should have been 0. So you go to 0. You can double check with 0 again, right? But you can actually just plug in one at a time and see if it's still satisfiable with that smaller formula. And then you gradually deduce the entire solution. So if you can just figure out yes, no, then all the bitcoins will be yours. Okay? So maybe one vote for the no is that if I knew how to do this, I would have all the bitcoins and I wouldn't be teaching right now. I'd be someplace warmer, although it's warmer today. Okay. Good. So, right, I prepared maybe a pro and cons list of things people might choose. I mean, I think on the pros camp, we should stress that this seems like the perfect problem for computers, right? It's just like very logical. Everything can be expressed as a tree. It's Boolean. Like this is like what computers are made for, right? So it just feels like at least the input format is very convenient. But the cons is, Boolean logic is potentially very expressive. We didn't do the full exercise of building a whole programming language, but we did some primitives that show that there's more than meets the eye. And there is some risk of being too good to be true. Okay. So, right. So in fact, we don't have an algorithm for solving Boolean formulas in general. Okay. Certainly, there's lots of interest. There's industries built around kind of more heuristic companies that try to solve Boolean formulas as well as possible. But there's no polynomial time guarantee. There's nothing that's as satisfactory as like the dynamic programming we did or the shortest path algorithms that we give. It says no matter the graph you give me, I can figure it out and it's going to be in some time polynomial on the size of the graph. We don't have any guarantee like this. Right? You can imagine like a company that focuses on formulas that come up in some kind of industrial design or something, and there's a lot of repeating patterns or, and it's a whole, lifetime of work. But as far as trying to get the kind of satisfying guarantees that we've been getting up to this point, that we still don't have, despite, we've all been tempted to be like, that looks so simple, and, try these ideas like that were enumerated. Well, can't you make some progress here? Can't you make some progress there? Yeah, maybe some of these heuristics work, but we can't really fully show that get you all the way to a solution. They're natural to do. They may be harmless in many cases, right? But that's far from being complete. Okay, so, all right, so that we don't have a answer to, but we can still ask like, okay, what about special cases? Okay, a specialization of the problem is not necessarily as hard, because if I solve a specialization, I don't necessarily solve the original problem. Okay, so here's a standard one. It's just, it's a certain kind of normalized style called conjunctive normal form. That means when you only have an and of ors. Okay, so all these individual clauses are ors of various things, and then you have ands connecting them. So if I were to draw a tree, it would always be very flat. There would be an there would be an and at the top, and then the second level would be ors over individual variables. Okay, so it's almost like as small as I can make it in a non-trivial kind of way, right? Okay, so the next big question, right, or the natural question, we can ask the same question for CNF-SAT. And the question is, if I told you that the formula was of this particularly nice and clean type, that if you expressed it as a tree, it would always be very shallow, right? So these kind of simpler class of formulas, can we at least solve these formulas? Maybe I can, all right, does the formula or does the setup make sense? I can very briefly ask this poll again. All right, so now we're doing CNF, so this is the flat version, okay? And so we can also ask for this one, whether you think this will be solvable or not, okay? All right, so first, who's not voting? It's always interesting to see if the number goes up. Oh, it went down. Okay. I'm doing something right. Okay. Who thinks that for the special case, we will come up with an algorithm? Okay. And who doesn't think we'll come up with an algorithm? Oh, I don't know how to count the TAs. Okay. Well, that adds up. Okay, it doesn't, but that's okay. That means that there are. Okay, good. So, but at least we're directionally aligned in the sense that this is a special case. So if you felt good about Boolean formulas, you should feel better about the special case, right? So it did go up. Okay, let's see what's right. Oh, I screwed this up. Okay. All right, so the more modest question is whether the polynomial time algorithm for this. Now, let's go back to our SAT programming language, right? These are not in conjunctive normal form. So conjunctive normal form needs to be like and of ors. Okay? And these equations we came up with, or at least that I had prepared ahead of time, are not in conjunctive normal form. In fact, they're both in the opposite, something called disjunctive normal form. Okay. Now, the question is, can we put each of these in conjunctive normal form? Maybe the first one we actually already did, or did we? No. Our XOR solution, I think, was already in conjunctive normal form. Okay, so looking at z equals x first, I just want to see if that's what we did. All right, so we wrote this. This was from applying De Morgan's law to XOR. And there, okay, so that would actually be a CNF for z is equal to x. Okay, so even in conjunctive normal form, you can still express assignment. Okay. Now, how about if x then y else z? Can we put that in conjunctive normal form? Okay. I see maybe some nods, but how? Partly because I'm kind of nervous to do this myself. I always mess this up. How do I turn this into conjunctive normal form? Yeah.
You basically just knot it twice, and then the first one you just
You knot it twice.
because if you do
I mean, if I do not, then isn't that just going to erase the
well,
knot?
it's
And
gonna
I'm
use like knot over it, and then you have it in a conjunctive normal form, and then whatever result you get from that, you knot it at the end, and then you get the same.
well, if you knot an entire conjunctive normal form, you don't necessarily get back a conjunctive normal form.
Well, but I guess I'm saying like whatever output you would get from, like if you knot that, you gotta go back to normal form.
Oh, okay. So I should maybe clarify. So in conjunctive normal, if I took a whole formula and then I put a knot in front, that doesn't count as conjunctive normal form. Yeah, yeah. So it has to really be like the knots need to be inside. Yeah. Okay. So yeah.
Distribute one side to the two other like variables of the other one.
Yeah. So we can start distributing them. I think this is also called De Morgan's laws. This must be another one of them. Anyone want to tell me how to do it? What should I write? Yeah.
If you do x and y and parentheses, with I think it's and x
And x not. Oh, or
then that entire thing is and then it's x plus
oh yeah, you're right. Okay, so we just go slowly and we kind of distribute things. Or z. So that's one step where I've taken the right side and then whatever algebra you once did in high school and distributed it over to 2 or discrete math or whatever. I assume we did this at some point. And then what? So we're not quite in conjunctive normal form yet. Yeah.
and say x or x rather
Yeah, so we can do the distribution inside each of these, gradually flattening it out. So we have x or x naught and y or x naught. And this would kind of be in a whole, one parentheses. And then x or z, okay, that's one parentheses. And y or z, I think that's hopefully correct. I mean, it should be mechanical. Yeah. Why don't you what? You can negate the whole statement, but then you'll get the negated statement. Okay, so now you look at this, and the nested parentheses actually dissolve because it's just an and inside ands and stuff like this. So, for example, this is XOR and X naught is always satisfied, so we can remove that. And we start erasing these outer parentheses. And I think what's left is an and of ors. Okay. All right, so okay, so that's what I had prepared. I meant to erase it and I forgot to erase it.
Using to transform it.
What logic am I using? Allegedly De Morgan's laws, but we're just distributing. Just sort of like A plus B times C plus D is equal to A, B, easy, this kind of thing. And just go slowly and you parse it, and then somehow it works out. Yeah.
By that logic, would you be able to convert every sat into a SAT?
Okay. By that logic, can I just always apply De Morgan's law until I always kind of flatten it out into this CNF state?
You just have product of sums by the end.
Yeah. So I can imagine taking any formula and doing this too, right? So that means any formula can be expressed as CNF. There is a catch. Well, yeah. So let me get up. Yeah. Okay. So okay. How about this? So I only mentioned the pros and cons still apply. I think same as SAT. Only maybe the too good to be true. We're a little bit less sure because it's more restrictive. And now getting to this question. Okay. So we want to show ultimately that a polynomial time algorithm for CNF SAT will give you a polynomial time algorithm for Boolean SAT. Okay, so we are going to try to prove this thing that I think we're kind of directionally going towards. And what that suggests, right, this is an interesting thing, it suggests that maybe CNF SAT is quite hard too. Boolean SAT maybe not so surprising because they can do any Boolean algebra, but now I even take a restriction and that's still too hard. And then I only wanted to point out the form by which we make this claim. What we're going to do is we're going to show that CNF SAT can be used to solve Boolean SAT. Right? So even in a situation where we can't come up with an algorithm, we can still say something very insightful. That this problem is as hard as that other problem by doing what we call a reduction. Okay, so we can still make progress even if it's not the kind of progress we've been making for the past 4 weeks. Okay, so in such a proof, one direction of the proof is very easy. Which direction is that? A CNF SAT is a special case of Boolean SAT. So if you can solve Boolean SAT, you automatically solve CNF SAT. That's not so interesting. The interesting direction is the opposite one. How do you argue that an algorithm for CNF SAT implies an algorithm for Boolean SAT? And I think maybe it's good to dwell on this question here only because it's our first time to even frame such a situation. Yeah.
If you can reliably come up with a system that can, I don't know what the best way to say it, but could consolidate Boolean SAT into SAT,
Yes.
then you would argue that an algorithm for CNF SAT would be hard.
Yeah. So we're doing something funny because we're kind of showing that an algorithm might not exist. Okay. For CNF SAT. But what we can do is we can presuppose what if an algorithm did exist? I just had this thing as a black box. We kind of did that as an exercise when trying to get all the Bitcoins, right? And then I say, well, I can take as input a Boolean SAT problem, which is some Boolean formula. And then maybe I can try to convert that input into an input for my black box, which only takes things in conjunctive normal form. And then, if it goes in, I have a polynomial time algorithm, I have a polynomial time algorithm overall, then, okay, this problem effectively solves that one up to polynomial running times, as far as polynomial running times are concerned. Okay. Now, I want to be a little bit more detailed about this. Okay. One thing that's important is that, because we're interested in algorithms that are like polynomial in the size of the input. Okay. So when I take my Boolean formula and I turn it into a CNF, I want to make sure the size isn't too much bigger. If I take a Boolean formula of size 100 and turn it into a CNF formula of size 2 to the 100 and plug it into the black box, no matter how fast the black box is, I'm not going to get a very good algorithm with respect to the original input. So we do want to be a little bit mindful of sort of how big our input is when we try to change it and how long it takes to even change the input, because that's sort of part of the pipeline, right? You start with some input to Boolean SAT, that's a Boolean formula. You have some code to process it and produce a CNF, and then you plug that into your black box. but the transformation is part of that pipeline. So you want to be mindful of how long the transformation takes and the size of your transformed problem, right? Because your black box only runs in some polynomial running time with respect to its own input size, not necessarily the original input size, so to speak. So, all right, so this all comes back to the suggestion from a few minutes ago. Okay. So I have a formula like this. This is that example of x1, x2, x3, x4, or the addition example, I think. And I want to turn it into a CNF. You know, this one's a little more complicated than the other one, so it's hard to just eyeball it. Okay. But the first suggestion is the most natural one. Why don't I just apply the Morgan's law and just kind of flatten the whole thing out, continuing to distribute until I end up with an and of ors. There is a catch, but what's the catch?
Is it too expensive?
Too expensive in particular, or a little more precisely? Yeah.
Exponential size.
Yeah, so if you keep distributing, right, the 2 by 2 will create like 4. And then you distribute 4 by 4 and you're creating like 16. And then, you know, because you're doing all this basically cross multiplying and stuff, right? So as in the layers, it can be exponential in the layers of the tree, right? So if you actually just applied De Morgan's law from top down, right, which is the most natural thing to do, it will blow up in size on you for, you know, certain very deep, you know, if it was a tree, very deep formulas. Okay. At the level of just doing assignment and if else, it's not that bad because that was sort of a small constant size. It went to a small constant size, right? So blowing up something really small is still moderately small. But if I give you something that's arbitrarily large and you start blowing up, now you're in a world of hurt. So just applying De Morgan's law and just kind of doing the arithmetic, the parenthesizing stuff, the algebra will not actually get us there. So any other ideas? I give you a Boolean formula like this. Clearly it's non-trivial, it's deep, it's uneven. I want to turn it into sort of like a flat thing. Yeah.
Just to understand, we're saying it has to be polynomial in the number of inputs, not number of operations in the tree.
Yeah, so at some level in this tree, you know, like basically just polynomial on the size of the tree. But there's many kind of equivalent ways to think of it. You know, the total number of leaves is basically a total number of nodes in a tree because all the nodes except for knots have 2 children and things like this. But basically just the size of the tree or the total number of symbols in the formula. So I think that's inputs plus symbols. I mean, that's what your computer processes, right? You get this long string describing a formula. You want something proportional to that size. Any ideas? This is guessable. It's very clever, but it's guessable. No, it's not a matter of like where you apply De Morgan's law. I think De Morgan's law will always take you to the same place no matter what. I think it's like idempotent or whatever. The order of operations isn't that important. Doing left tree or right tree first, it won't matter. Yeah.
And instead of breaking it down into more things, we could instead compress operations into.
All right. Can you compress?
Like idea of like how we compress SECs and graphs. Like
Oh, well, yeah. Can you try to find maybe some logical tautologies or redundancies and just prune it? Maybe, but I don't know if that can take you all the way. At some level, that also sounds like an algorithm just trying to solve the thing, right? You're trying to really break up the structure. So maybe as a hint, you are allowed to do things like add new variables, as long as the overall size comes out okay. So, which is more degrees of freedom than you're allowed in the usual purely math point of view, just doing De Morgan's law. Yeah.
If we want to add variables like that, wouldn't that let us decrease the amount of complexity because we're turning a deep tree into a shallow one?
Okay.
Since, I mean, as I recall, was when you have this or that, and going out through a bunch of layers, as you need to account for all possible cases. But if you add a variable like random one and have it true on one side, on the other side or something like that, then it would let you kind of decrease the amount of different the options that you need, since it lets you kind of ensure that only one or the other ones will be chosen right in those hands.
So I think the key word I'm honing in on is that you said I can name this branch 1, right? And just like, oh, this is branch 1, and I worry about branch 1 elsewhere or something like this, right?
Yeah.
Does that inspire any ideas for kind of what to actually do step by step? And naming is a useful word here. All right, so let's take this branch here, right? What I can do is we can make a new variable z1, and it'll be equal to whatever this is. And then I'll insert z1 right here. Yeah, I just took a subtree and pulled it out. We know how to do assignment, right? We know how to do z1 is equal to x. X is a little bit more complicated because it's an and of 4 different things. Okay, so I can just gradually pull out pieces of this tree. This can be z2. Okay, and whatever that comes out to be. I messed that up. Oops. Okay. This tree can be like z3. I can call this z3, and I'll write down whatever formula does the assignment for me, using our SAT programming language, right? We know how to do that in conjunctive normal form. I can pull out this tree, right? And I'll call this z4, something like this. And I can imagine going one by one, just pulling out little trees, little trees, little trees. Each of these represents some small CNF, right? We can always use De Morgan's law, but they're small, so it won't blow up that much. They're not that deep, right? Because I'm pulling out one layer at a time, yeah?
Yeah, before you mentioned that when you have the same variable in different ranges, like that can cause some confusion. It's not as separate as it might seem. Does that not impact what we're doing here with the?
Yeah, I mean, I think we should have faith in our SAP programming language and that it's correct, right? So what we want to argue is that each individual operation doesn't change anything. Maybe first I should just show like a final product. Well, okay, if you want, you can first make it into a binary tree if you really want to make sure it's nice and small. But maybe I'll come back to that. Okay, so what you can do is you can go through and you insert all these, first I turned the tree, which had originally like degree 4 and stuff. I made that into a binary tree just as a cleaner pre-processing step. We can go back to that slide in a moment. But then I've introduced all these variables. So like x7 is going to be equal to x1 or x2, okay? And so I want to make sure I'm kind of encoding that logically. So that should map to, I think that's this one here. So I think this line here will be this part here. Okay? So I think what this line here says is that x1 needs to be equal to the value of x1 or x2. Okay? Otherwise this line will come out to be false. So I'm just plugging and playing with our SAT programming language where I knew how to set z is equal to x. And here, x is a little more complicated. It's x1 or x2. Okay? And I'm going to take the conjunction of all of them. So since everything has to be true to satisfy the whole thing, so I've kind of omitted sort of the ands from the line wrapping. Okay? So everything needs to be true. What I've done though is I've taken the tree and I've just kind of ripped it apart into individual little statements. And these are all semantically representing some kind of assignment as I pull out one tree, pull out one subtree, pull out one subtree, pull out one subtree. So I can only make this thing true, right, if I also follow all the rules of the assignment. So that means x7 has to be equal to x1 or x2, or else this line will come out false and I won't satisfy the whole thing. Okay, so these constraints are, that's how sort of the programming language functions, so to speak. Right? So the constraints are making sure I'm honest and not changing any of the satisfiability of the formula. Okay. So you can go through, say, one of these, because I think one is enough to make the point. If I want to write something like x1 is equal to x2 and x3, okay? And we just plug in what we had done before, I guess you'll initially get something like x1 or this thing negated. Okay. And this thing or x1 not. So here I'm just plugging in whatever formula we came up with before for z equals x. It's just that x is this combination of two things, so it looks a little more complicated. And then I guess we just do like the De Morgan's law thing. So you start getting like x1 or not x2 or not x3. And, oh, maybe this was, x2 or not x1 and x3. I'm only like mildly sure I'm doing this correctly, but it's not that important that it's totally precise. What matters is that it's just a small thing involving a few symbols. And so at that level, I can still do De Morgan's law. Even if it blows up on me, it's just going to go from a constant to a constant. Okay, so from here, we can just do the mechanical thing at a small level, at a local level, to get the conjunctive normal form. Okay, so as soon as I can just do this assignment, now I can rip apart the whole tree. And each of those steps, I'm not losing any correctness. One or another, yeah.
Doesn't this still kind of blow up the number of elements?
Okay, that's good to count. So, because this formula looks a bit big, right? I mean, it's quite daunting. But I want to argue that it's not that much bigger. How? Yeah.
And if we could argue that an upper bound would be reassign every internal node as a variable.
Yeah, so we can account it just like relative to the tree. So first I took my, uneven tree and made it everything degree 2. That won't dramatically change anything, right? Because, as long as like, if you have a binary tree with n leaves, you're only going to have like 2 n nodes or something. So that's not a big deal. And now what we've done is every one of these internal nodes that creates an assignment got turned into 3 relatively small clauses, right? So for every internal node, I just wrote like 10 letters or something. So it's a small constant size formula for every node. There's big O of n nodes, or something proportional to the original size of the formula. So overall, even though this looks quite messy and harder to parse compared to the original tree maybe, it's only going to be a constant factor bigger. So the size didn't blow up on us that much. Yeah? Okay, any questions? So, yeah.
So the tree that I was saying x7 and x9. So if I differentiate to that, it would be one of
Okay, this is not a very clever thing because x7 and x9 are the same tree. I could have assigned it. Yeah, but in the worst case, it's hard to say that it's going to make a significant difference. Plus, we're not really, we're only increasing the size by a constant anyway. That's about as good as you're going to get. So I only want to know, I won't go through all the details, but to fully formalize this proof, you want to show your reduction works. So what you really want to show ultimately is that if your Boolean formula is satisfiable, then this CNF formula is satisfiable. And if your CNF formula is satisfiable, then the Boolean formula is satisfiable. So this way, yes means yes and no means no. And the first thing we'll check is like, did they at least do both directions? Because also it's like very easy to like accidentally do the same direction twice and stuff if you don't go slow enough. So in general, it's not that bad, but you just want to make sure you go slowly. Under time pressure, you might mess it up, but if you go slowly, keep your logic straight. Okay? But then that will really show it's sound and complete. So that overall your pipeline, if your pipeline between transforming and applying the black box says yes, it really means yes. If it says no, it really means no with respect to the original problem. If you just kind of think through what's necessary, the proof is basically checking the two sides. Okay, maybe I'll just run quickly through the last parts. All right, an even more special case would be 3-sat. That's like CNF, but I promise there's only 3 variables inside each clause, so no very wide variable clauses. Anyone think we'll have an algorithm for this one? Just by show of hands. Does everyone else think that it's going to be just as hard? Okay, 1-0. So, in fact, if we looked here, even this solution here, we took a general Boolean formula and made something with at most 3 variables, right? But this is 2 or 3. If I was insistent upon getting exactly 3 variables per clause, that's even more special, right? Any ideas? So I just want to figure out how to turn the 2 variable clauses into some 3 variable clauses. So I'm not going very slow in the interest of time.
Or
Sorry?
you should add or one.
Well, it has to be a variable. You can't add a, you would probably add or false, but you're not allowed to put in a literal. Yeah. No, well, 3 distinct variables. Any ideas? Going once, going twice. I know you'd rather get out of here, so I'll just give you the answer. What you can do is you can just use the same variable twice, but in one you'll put it positive, and the other you'll put it negative. Right, so this new variable a you introduce, it's only going to help you in one of the 2, and then the other one, you have to actually satisfy the original 2 variable clause. Okay, so that's a quick trick. And then lastly, I would have gone through more slowly. There's one more problem of circuit sat, right? So this is even more general than Boolean formulas because this is not necessarily a tree. This is a DAG. That's more general, right? I won't even bother taking a poll. Circuit sat is the same ultimately as Boolean sat. Of course, circuit sat is more general than Boolean sat. But how can I use Boolean sat to solve circuit sat? So here's a circuit. And I want to turn to a Boolean formula. You can even turn it into a CNF.
Each of the sides,
Sorry?
like each of the source from the graph, so it's like the input of the
So we can do just the same trick. Z1 is equal to this, Z2 is equal to this. So all those intermediate values we'll just assign to new variables. And we'll do the exact same thing we just did in going from Boolean formula sets. In fact, the exact same thing will work. And I won't do the details because we're already out of time. Let me just, sorry, you don't like it when I say let me just, what's the key point? So these are all really basic, simple problems. Like Boolean formulas are very simple. They're perfect for computers. We would love to have algorithms for them. And we don't. And people try very hard. This whole industry is built around this. Plus, you would like to get all the Bitcoins. What's interesting about this lecture is that although we didn't solve any of these, we didn't come up with any new algorithms, we were still able to say something very precise about them, right? We're able to say that like 3-SAT is just as hard as circuit SAT or Boolean SAT. If you can solve 3-SAT, you can solve Boolean SAT in the opposite direction, so kind of more obvious. So we can start at least relating these problems in a very precise way. Yeah? So in this sense, we're still making a lot of progress. We're making a lot of insight, even though we're not walking away with, an MN time algorithm or something. Okay, so we're going to do a lot more of that. Mixed in was also coming up with some algorithms for the next few weeks. There's another dimension. Okay, thank you.